Okay, I'm very glad to conduct second part of today's session. And the first speaker is Yegor Zenkevich. He will speak about uh, aromatics of Hanani-Witten.
Okay, thank you very much. And I would like also to thank the organizers for giving me the opportunity to give a talk here. It is always a great pleasure to be on this workshops in Trieste. So I will describe a certain construction, a certain algebraic construction, which has to do with brain webs and brain backgrounds in string theory. So let me start with some physical part, and then I'll switch to the algebraic part, because the main, well, I'm going to give, there will be a particular example of this construction, this funny type of NUR matrix for a certain algebra, and but the idea is to give a dictionary between the brain constructions and the algebraic constructions. So I start with the brains of type 2B string theory. So I'm going to consider a type 2B background. So the 10 dimensions of the setup I'm going to put in a table like this. So I have 6 dimensions, which I split as 3 complex dimensions, and there is going to be equivariance, like a omega background in these directions, with Q, T inverse, and T over Q parameters, so that in total it preserves the Calabi-Yau form on this C3. So this gives me 6 dimensions. And there are 4 dimensions left in string theory, so this are going to be denoted by Rx, Ry, R tau, and a circle. So this circle, it takes part in the omega background along this 3 directions, so that if I go along this, around the circle, these complex directions are multiplied by the corresponding parameters, Q, T inverse, and T over Q. Okay? And this S1 is not really going to take part in the pictures I'm going to draw next, the brain pictures. I'm going to draw a lot of pictures in this talk, but this S1 is not going to take part in them. I will show you in a moment. What I'm going to draw is essentially this 3-dimensional space and this projection on the XY plane. Okay. So what are the brains of type 2B string theory? Well, there is naturally a zoo of brains. There are like even-dimensional brains, like D1, F1, D3, D5, and S5, 7 brains, like D7. So there is a whole zoo. Now I'm going to argue that all of the zoo is captured by a certain algebraic structure, but particularly today I'm going to focus on these 2. So let me make brief comments about these 2 ends of the spectrum. So D1 and F1 are going to be built into the algebra, so they will correspond to the generators of my algebra, and I'm not going to have they will be well, the counting of them will be automatic in this construction, and D7 is just a bit too complicated for this talk, so it can be described, but I'm not going to talk about it. So I'm going to focus on these 2 cases, and let me start with drawing these brains and drawing some pictures with them. So if let me start with D5 and NS5, like what else can we have? So this a bit more generally, they belong to the family of PQ branes. So this together, they are PQ branes. So D5 is going to be 0, 1. So let me draw it here, 0, 1, and NS5 is going to be 1, 0 brane. So in type 2b there is a complete symmetry between them, a duality symmetry between them. So the D5 is 6-dimensional, and in this picture with Amiga background, in this equivalent directions, like in these directions in which the equivalence acts, it can either span a whole complex plane or be a point at the origin in the complex plane. So we have to choose which directions we are going to span, and it turns out that for reasons of supersymmetry, one needs to choose 2 complex directions out of 3. So in this case, I'm going to choose Q and T inverse and label my brane accordingly. So this is not on any choice is possible. So here, just to make an explicit example, I choose something. And here I'm going to have to span one direction, and I'm going to span S1. So why I said I didn't care too much about this S1? Because all the branes I consider are going to span this S1. So nothing will happen in this direction. I cannot comment on this. I don't know the real reason why you cannot generalize to. Yes. So there is no equivalence along this line along this direction. So I guess that's the reason why you have to have the product of factors here equal to 1. But this is a crude explanation. I can always, well, I'm tempted to say that for reasons of supersymmetry, but I'm not really prepared to comment on this, unfortunately. So this is one of the branes we are going to consider. So there is also NS5, and you can let me draw it like this. It is also going to span the same directions. Again, this is a choice, and I'm going to comment on this in a moment. I'm going to talk about different choices in a moment. What is essential is the types of branes here, they correspond to the directions in which they go in this XY plane. Okay, so D5s are going to be pictured vertical, and S5s are going to be pictured horizontal. And this is what I'm going to draw on the blackboard. Now, when I have a vertical and horizontal lines, which represent 5 branes. So, of course, I can consider and I can ask myself what happens at the junction, and the junction is possible in this type 2b setup, giving rise to so-called PQ brane webs. So one can join a bunch of D5 and NS5 branes, giving rise to pictures like that. This is one prototypical example of a junction of different 5 branes. So in particular, here the horizontal one again is an NS5 brane. So this is NS5 or 1, 0 brane. This is 0, 1, and when they're joined, this is 1, 1, which doesn't have a specific name, but it is also an object in this theory. So these diagrams, they are interesting not only from just string theory point of view, but they give rise to 5D n equal 1 gauge theories. Well, not every diagram, but a large class of diagrams encodes the matter content of 5D n=1 gauge theories, which live on the world volumes of this D5 branes, like those 5 branes in general. So where are these 5 dimensions? They are this and this on CQ times CT inverse times S1. And these gauge theories, they have partition functions which were computed by Nekrasov. So 5D Nekrasov partition functions which were computed by localization, and they depend on Coulomb range parameters and couplings. So, yes?
Why are you saying that 5D? What about Rx and Ry direction?
The branes are these segments on which the theory lives, they are finite in XY direction. So these are going to be in IR, they are not going to be visible. So the theory here, for example, it really lives on these 2 segments of D5 branes. So there are 2 parallel D5 branes which have finite span in this Y direction. So it is going to be dimensionally reduced on that, on 5-dimensional space. Since there are two of them, is going to carry SU2 gauge theory or U2 gauge theory. So in this particular picture, this is a U2 plus 4 fundamental multiplets.
But also the segments that look like semi-infinite, they're also finite?
These ones?
Yeah.
No, they're really infinite. So they correspond to the sort of, if you wish, a frozen gauge groups which correspond to these fundamentals. So you can draw a quiver for this theory like that. It is convenient to draw it like that. Split these 4 fundamentals into 2 pairs. So this 2 lives here. So this part corresponds to this 2. So this pair of semi-infinite D5 branes correspond to a frozen node, and this pair corresponds to another frozen node. So this is a crude cartoon of how this brane picture corresponds to the quiver of the theory. Well, that's because in gauge theory we look at things not in an SL2Z invariant way. We forget about SL2Z symmetry of string theory, and we look in a particular expansion in a particular way on the theory.
From the picture, how can you see it?
There is no way to see it in the picture. The picture is completely symmetric. Exactly. In gauge theory, like in the picture doesn't know about your.
Also, you said about Coulomb parameters and couplings, and there are masses.
And masses, of course, yes. So, thank you. So Coulomb. Yes, thank you. Coulomb range parameters, couplings, and masses. Again, as you correctly pointed out, they can be thought of on equal footing with Coulomb range parameters. Really, they're just frozen Coulomb range parameters. And then what they correspond to in the picture are these lengths of these segments, because you can adjust picture a little bit, and this corresponds to changing of these parameters. I can be more specific, which ones are Coulomb, which ones are masses, but let us just remember the important point is that the lengths in this picture are fixed by the parameters of the gauge theory. The Coulomb range, in particular, I'm going to talk about Coulomb range parameters. So the moduli of this picture, the subset of moduli of this picture, they correspond to walking along the Coulomb range. And the Z nature depends on them. in a funny way, but the natural question then is to ask what happens if I go to the Higgs branch now. So going to the Higgs branch corresponds to reducing this length to 0 and this length to 0, and then moving one of the branes out of this picture. Okay, let me draw it like this. So I'm going to have a picture like that. Sorry. So this is going to be a Higgs branch of this theory. This corresponds to going to a particular point in the Coulomb, on the Coulomb branch, where these two branes, they are no longer broken. So it is one unbroken line, and then moving this line out of the plane of the blackboard, which correspond to moving these branes along this line, RT. Okay, so this brane is going to sit on top of this plane of the picture at a different value of R tau. Now, what happens to, yes?
So the Coulomb branch of this initial theory, how many complex codimensional one singularities does it have? Is it 8?
Complex codimensional.
Conical points. How many? Because local at 0 is 4, but then you have 4 masses. So is it 8 of them? Are you going to one of these conical points to go to the Higgs branch?
Yes, I do. Well, okay, so it depends on, like, if you want to vary, you need to adjust masses, right? To be able to go to the Higgs branch, to the origin of the Higgs branch, you have to adjust the masses. So if you count all the parameters like Coulomb branch and masses, then you should adjust both of this. Okay, to the counting, I'm not sure I can like say it right away how many singular points like that, because you can also adjust this one and that one. You have to do a little bit of combinatorics. I'm sorry, like choosing 2 out of 4, I guess. Okay, sorry. So this is what happens. You move this brane out. Now, what happens to the partition function? So Z is constant on Higgs branch. So when I came to this origin of the Higgs branch to a particular point on the Coulomb branch, like I have 2 branches joining, as usual, this picture is drawn. I'm sorry, I'm not giving any references or such, because I just want to spare a little bit of time, but this is all very, very classical results from the 90s and maybe earlier, I don't know. So this is supposed to be Higgs branch. This is supposed to picture the Coulomb branch. I go to this origin of the Coulomb branch, then I move my brane out, and Z remains constant, so it doesn't depend on the tau direction. And this tau direction is for these observables is sort of topological. Nothing depends on the particular placement of this branes along this tau direction. Okay. Now, what you can have when you've moved this brane out is to add a bunch of D3 branes. But one can add D3 branes, which play the role of vortices, vortex solutions in 5D gauge theory. So they have vortex solutions in the 5D gauge theory, but also on the world volume, there lives a 3D theory. So how can I picture them? They are going to be like that. So there can be several of them here, several of them there. So this determines the type of this vortex solution. And in this diagram, these D3s, they are 4-dimensional, and they are going to span this RT direction. So as here, you have to have a little bit of 3D imagination that to understand that this guy is somewhere, like, levitates somewhere here, and then you have these dashed lines representing D3s. They stretch between the plane of the picture and this levitating brain here. Okay, so this D3, it spans RT direction, the direction perpendicular to the blackboard, and also it, as I promised, is going to be to span this as one, and one of the complex dimensions you have to choose, but you have to choose wisely, because you cannot choose the direction this one, because then it will not be able to join my five brains. So I have to choose either Q or T inverse. So for example, I choose Q, and then I have this D3 Qs here in my diagram.
Sorry,
yes.
Picture, can we extract information about any parameters of this Higgs branch? What are the parameters of this picture? Like, similarly on top, you have this distance equal to
So this distance in the t direction, I cannot like say right away which operator, average of which operator it is, but it is some coordinate on the Higgs branch. One real. Yeah, as far as I understand.
And Higgs branch should be at least 4-dimensional. Yeah. Where are others?
Should it be 4-dimensional? Okay, so yeah. There should be some parameters not visible immediately on the picture, and probably they are related to certain fluxes of the gauge field, but I cannot say right away. This one. Now this is the I think this is a Coulomb range this is coupling really of the gauge theory. Yeah. So yeah, I'm sorry. I have to find 3 more, but yeah, I have to ask some experts really. So I'm sorry. So the reason for this introduction is really to have a correspondence with the algebraic part, of course, and yeah, essentially everything depends on this distance only. Okay, so we have a bunch of D3 brains stretched here, and this gives rise to some vortices, which on the world volume they carry a 3D gauge theory. Yes. Sure. Yes.
So the number of D3s that you put on either leg is up to you, right?
Yeah.
And can you also Higgs the other half of the diagram at the same time?
Yeah.
Okay.
Sure.
What are you left with then? Because you already Higgs all the gauge symmetry.
Yes.
So what happens in field theory?
So I think in gauge theory, so you, strictly speaking, you are still left with some U1 gauge symmetry here. I think then you Higgs that. So that was a U2 theory. Yeah. So on this D3 brains leaves a 3D n equal to 2 gauge theory. Okay. So far I had everything here, all these brains here, D5 and NS5 and 1, 1, they were all of the same type in terms of this Q and T inverse. And this is what PQ brain web tells us, because only brains of the same type, I mean the same type in the sense of this Q and T inverse, can merge together. So if I say that there is a PQ brain web, then I immediately know that all the brains on this picture span CQ and CT inverse. Well, anyway, they span the same pair of complex directions here. Now, if I say that I have extra brains like D5Q and T over Q, which spans a different pair, like that. Sorry. Well, I hope it's understandable. Then these two guys cannot merge, though this one is horizontal, this one is vertical in the picture, but they are of different type and they cannot merge. Now, what can happen is that they can lie in different planes at different values of tau, like here. So in this picture, this brain can be replaced by a D5Q T over Q, which will give rise to an, if I replace all of these D5s, like Pietro said about the complete Higgsing, like if I also Higgs this one, say like that, or better like that, it can pass behind, like that. If I trade all of them for this D5 T over Q, then this will enhance my supersymmetry for the 3D gauge theory. So this is going to be 3D n equal 4 gauge theory on the vortices. And this is the setup which was considered by Hanani and Witten. Also in the 90s. So far I gave a review of basically what, well, apart from this Nekrasov function, this was like a review of things which happened in the 90s. Now, I'm going to translate all these pictures into formulas now. And this will be the job of the algebraic formalism I'm going to introduce. And every part of physics here is going to correspond to certain algebraic fact or algebraic things happening. So I guess I cannot use that blackboard. Nobody is going to see it. Okay, so I try to erase gradually, things gradually. Now, algebraic formalism. And I will not go into too much details because it's very technical, but everything can be made very precise here. So the first and the most important ingredient here is the algebra itself. So the algebra is this quantum toroidal algebra. I'm not going to write any commutation relations or generators. It's just a huge algebra. That's what is important to know. And this is the algebra of D1 and F1 brains. So some of you may have heard about the BPS algebra, the algebra of BPS states. So here it is precisely that, but in a string, type 2B string theory, D1 and F1 brains are BPS states, and this is presumably, so this is a conjecture, that this is the algebra of these BPS states. Now, what does it mean? It means that branes are representations of this algebra. Let me denote it by A, since it's cumbersome to write out all these indices and heads. Now, branes are going to be representations, and 5 branes are going to be Fock representations, and 3 branes are going to be a different type of representation called vector representation. Fock representations are, well, it's the important mnemonic is to remember that the states of these representations are instantons. Instantons is the 5D gauge theory. So the instantons, fixed points in the instanton modular spaces, are Young diagrams. So this lambda is a Young diagram. And these are precisely the states in the, well, K-theory of, equivalent K-theory of the modular space of instantons on the CQ and CT inverse. So the Q and T parameters, they're exactly the equivalence parameters of this. So this is the same space as features in the works of Nakajima, for example. Now, 3 branes.
What are the parameters of these 5 branes which are identified with set of parameters of this Fock space representation?
The positions. You have the positions. If you have a horizontal brane, then you can still move it in this direction. Well, it gets complexified by the flux. So in this case, I don't know the answer. So it gets complexified by the flux of the gauge field living on the brane along around this S1. So you have U1 gauge field, and there is an additional phase. So it's a complex number. So this is some U, which is the complexified position of the brane, and in the algebraic formalism, this is going to correspond to the so-called spectral parameter or momentum of this free boson-Fock space. Okay. Now, 3 branes, they correspond to states being labeled by sort of 1D Young diagrams, which are just numbers. Yes.
Instantons for the 5 branes actually are, at least for the 5s, are the watts, no? So,
Yes.
So why you're saying that the Young diagrams are describing the 5 branes?
Yes, it's a bound state by bound state. So you have a single. Yes. So the 5s are representations. Like if you you have a representation, but you act on it and you change the states. So the states are bound states of the one with something, and the something with which you bind the one determines your representations. There are options. So vector representations, the states are labeled by one-dimensional Young diagrams, which are just integers, integer numbers. This is not the details are not important, but the idea is important that the representations do correspond to higher dimensional branes, like 3 and 5 branes and 7 branes too. Now, what happens with the pictures? The pictures, they correspond to intertwining operators. And this is an also quite, by now, quite old work of Awata, Feigin, and Shraishe, that you can have an operator acting from a tensor product of 2 representations into the third one, satisfying the intertwining condition. Like the simple model for this is if you have an SU2 algebra. So, toy model. Just for people who are not like so much into infinite dimensional algebras, the toy model is for SU2, there are Vn finite dimensional representations, n-dimensional n-dimensional irreducible representations, and one can take a tensor product of two of these guys, and this is going to be expanded into irreducibles again. So there is an operator psi nmk, which acts from Vn tensor Vm, projects it out on a factor with fixed k. Okay? Now the same thing happens here. This is going to correspond to an operator acting from F tensor F into F again, just in the same way as in the Stoa example, and these Fock spaces are going to correspond to this pair of Focks of 5 branes, and this is going to correspond to this one. They're all going to be of the same type, what is important. So this F's do have indices QT inverse, and these indices must be the same. Otherwise, such an operator psi does not exist. And this, of course, fits in with the string theory picture that only the branes which have the same parameters can actually join. Okay, now I can combine these operators and get a larger, like a larger combination of them. Like if I combine them in the picture which I have just erased, I'm going to get an operator which acts from a bunch of Fock spaces into another bunch of Fock spaces. So this is the same picture, just with arrows indicating in which direction the operators act. So I'm going to have this 1, 2, 3, 4 Fock spaces ingoing, and 1, 2, 3, 4, sorry, 1, 2, 3, 4, yeah, Fock spaces incoming, and 1, 2, 3, 4 Fock spaces outgoing. So this is going to be an operator from a fourth power of F into fourth power of F. Now, if I plug in the highest weight vector in the Fock space, also known as the vacuum, I get a number. So this is no longer an operator. This is a number. And this number is just equal to 5D Nekrasov partition function. It depends on the same variables, because this F representations, they depend on U, on the spectral parameters, which correspond to the lengths of the intervals. And the answer turns out to be the same. This is this was also discovered by Awata, Fagin, and Shiraishi. Now we come to something which was not discovered by Awata, Fagin, and Shiraishi. And this is what happens when you Higgs your theory, when you go to the Higgs branch. So when you go to the Higgs branch, you should do basically the same, like you have to collapse these segments and see what happens. It turns out what happens in the algebra is quite interesting. Now, I hope it's visible here. So Higgs branch it gives rise to R matrices. So R matrices are brane crossings. And one can find them explicitly. So if I draw something like that, this is supposed to represent a brane picture here. And one can ask, what is the consistent way to plug in an operator? So this is going to be an operator from a Fock space tensor Fock space, two incoming lines, into Fock space tensor Fock space outgoing lines. What is this operator? One can just start experimenting and see what are the degenerate values of this operator. This crossing and that crossing, which lead to the correct expressions for the partition function and which satisfy the usual properties. And the answer is that there is such an operator called an R matrix of the algebra. So R matrix of the algebra A. So algebra A is super complicated, but in these particular representations, Fock representations, with this vertical and horizontal ones, one can explicitly compute it. And I have an explicit expression for it, which, of course, I'm not going to write out. But you can check out the papers, and it isn't there. Now, this makes all this brain picture look like a Chern-Simons theory, because you have a 3D space in which there are lines, and these lines can cross, like go on top of each other. It seems that this would correspond to an operator which is basically a permutation. Like these brains are far away. Nothing depends on tau, on the separation in tau direction. So here in this picture, I have, I have a separation delta tau between the planes in which these two brains lie and this brain lies. Nothing depends on this delta tau, so it can be made arbitrarily large. And it seems that this operator should be just permutation. But as we know from Chern-Simons theory, the for topological, for example, theories, this is not always the correct intuition, that you do have a non-trivial operation corresponding to crossing of line defects. So here is precisely this situation. So I've told you that nothing depends on delta tau, but this is not really precise statement. So in fact, I should say there is a piecewise constant dependence on delta tau. What does it mean, piecewise constant? So if delta tau is positive, this is going to be the R matrix. If delta tau is negative, it's going to be the inverse R matrix.
Yegor, in Chern-Simons you also have the skin relation that relates the two.
Well, it depends on your representation. If you are in fundamental representation, there is, but in general, there is no. So here, I don't know any such relation, but to hope to have scaling relations means that you really have to understand, to take in some way the simplest possible representations on your line defects. And even then, it's not guaranteed. That's true. That's true. So I don't know. There is one relation which I'm going to give at the end, which looks very much like a scaling relation, but not exactly. So I have two different pictures, like this one and like that one. So this is R, going to be R. This is going to be R inverse. So I have two operators, and everything, if I plug them into my picture, brain picture for the Higgs branch, everything turns out to be consistent. The R matrices are consistent, and I can move between these two pictures. And this, in the end, this gives the correct Nekrasov partition function, the correct answer for the Higgs branch partition function. Now one can go further and stretch D3 brains between them. You have to combine, just as you did here, you have to plug, instead of the circled pieces, the R matrices, the corresponding R matrices, and then take vacuum matrix element of the whole. and this will give you the correct answer. So yeah. Now if I put some more D3 branes in here, I can model my 3D n equal 2 gauge theories, which live on the vortices. So I can have pictures like that. Sorry. Where this guy corresponds to a D3 brane, but it also, in the algebraic picture, it is going to be a vector representation. And again, I'm not giving explicit answers, but they exist. And these brane junctions, they are also given by some explicit formulas, which are analogs of this Awata-Feigen-Sharaisha operator, but for junction of a D3 brane here with a 5 brane. Okay, and this reproduces partition function of 3D n equal 2 theories living on the branes. Now, these R matrices can be obtained from the degeneration of these circled pieces when I shrink this cycle here.
Sorry,
Yes.
The 3D partition function emerges if you put the vacuum.
Yes. You have to put vacuum everywhere. Yes. So now the last piece I'm going to talk about is the R matrix corresponding to these two branes being of different types, as emphasized here, like as pictured here in this table. If they are of different type, one cannot obtain them by shrinking the cycle in this known PQ brane web. You have to find them from scratch. And it turns out that one can really do it. So there are brane crossings for branes of different type. So the last piece, so this I call Hanani-Witten R matrices. And let me emphasize that my guiding principle, what constrains my operators, is this algebra A and the algebraic properties which the R matrices should satisfy. That there should be unique operators satisfying this R matrix properties for a pair of Fock representations of different types. So since I don't have different colors, I have to invent something. So let this be Fock spaces of different types. So this is F QT inverse, and this is FQ T over Q. So this is also going to be the R matrix evaluated in the corresponding tensor product of representations. Now, I obtain an explicit formula for this. It turns out to be a very funny combinatorial expression. I don't have time to elaborate on that. But let me just emphasize some properties of this R matrix. So it gives, if I plug it into my picture, just like here, and connect it, connect the branes here using some my analogs of D3 branes, I get a 3D n equal 4 gauge theory partition function, just in the same way as I did using the vacuum matrix element. So I can draw pictures like that. This one, and then I can have whatever can happen here, like that. And then I can have a bunch of these D3s here. This will give me a partition function of certain 3D gauge theory. Let us even forget about this piece and just focus on that one. So Hanani and Witten told us how this theory should look like. In particular, these brane junctions should satisfy certain rules, certain properties, which are known as Hanani-Witten rules or Hanani-Witten moves. For example, the crucial point for this construction to work, the brane construction to work, is that the two operators which are R and R inverse, they're actually related. So this is R inverse, evaluated in this pair of representations. For Hanani-Witten, it turns out that they conjecture that whenever you cross a brane, you pass one brane in front of the other, behind the other. There is a singular point when they actually touch, and at this point, something murky happens. But the end result is that there is an extra D3 brane here. Okay. Now, naturally, I do have an expression for this junction of D3 branes. So I have to write in the right-hand side, instead of just R inverse, I have to write something like F tensor F star, which correspond to these 2 points. So this phi and phi star, they correspond to these 2-point junctions. And then Hanani-Witten tells us that these two lead to the same physics, the same 3D gauge theory in the IR. That's one of the main points of the work. What I observe is that these two are equal. If I construct everything according to the algebra, the R matrix is unique, everything is unique. Like this phi is also dictated by the algebra, but this identity is not dictated by the algebra. It is a property of this particular pair of representations, and, well, you couldn't have guessed it. But it turns out to be true. So these two brane pictures are equivalent, and these two expressions are equal. And this is an extremely non-trivial test of this dictionary between the branes and algebra, brane junctions and intertwining operators. So everything fits. And another peculiarity of this Zenkevich setup is that you cannot have, according to the work, you cannot have more than one D3 brane here. So the picture like that, with a pair of D3 branes. So you have a pair of D3 branes here, should not be possible. So recall that I draw some of these pictures here. I could have drawn a pair of D3 branes here, but that was a different situation, because these 5 branes were of the same type. But here I have this fat 5 brane, and Zenkevich tells us that this should be excluded. And it turns out that indeed this is equal to 0 in the algebra as an operator. Or in other words, the corresponding intertwining operator turns out to be non-existent. There is no operator like this. So Hanani-Witten rule and Hanani-Witten move, they are satisfied. So this is called the Hanani-Witten rule usually, and this is the Hanani-Witten move. So they are both satisfied in the algebraic language. Okay, I still have like 4 minutes. So I'm going to write out to scare you a bit more, or bore you a little bit more, and to actually give a sketch of the expression for this R. And then to give, like, it's not just because I enjoy the formulas, but because it leads to some funny combinatorics. I actually write out both. So I have this R, let me call it R n equal to 2, and I have R n equal to 4. So this is the Hanani-Witten situation, like 3D n equal 4, 3D n equal 2. This is the one obtained from PQ brain webs. And this one cannot be obtained from PQ brain webs, but instead corresponds to this Hanani-Witten setup. Now, I'm not going to give a full expression, but let me just give you an important property of it. If I put lambda and mu states here, these are fixed points on the instant and moderate space. So these is a pair of Young diagrams. So this corresponds to taking a partial matrix element of this R. It's a matrix element along one of the representations, one of the legs. And I do the same here. So I have a fat brain here. And this brain there. So this turns out to be not zero, only if and only if lambda mu fits inside lambda. So this is a selection rule for this. And matrix elements, well, there are explicit matrix elements for this case. So the expression is known. I'm just not going to write it out. But the important point is that in other cases it vanishes. So from lots of pairs of lambda and mu, it vanishes. And here, it turns out that the condition is much stronger. So what does this mean? This means this is called an interlacing condition. Interlacing. What does it mean? It means lambda is less than mu1, is less than lambda 2, is less than mu2, etc. So if you forget about this, then it is just this condition. But for interlacing diagrams, I have these extra conditions. And this constrains this lambda and mu diagrams a lot and plays a crucial role in the proof of this identity. Now, just a hint. This is just a hint on the structure, but let me also give a hint on the application of this structure. So this interlacing condition is very funny because it. So I have to finish in a minute. In just 1 minute, okay? So this interlacing condition plays a role in 3D Young diagrams. Because if you imagine a 3D Young diagram, so hint, a 3D Young diagram is a collection of boxes in an angle here. And I can draw it somewhat like this. And then I cut it with diagonal planes. In every plane, I have a 2D Young diagram here. This gives me a lambda diagram, say on this slice, and on the next slice, some other diagram mu. So if I have neighboring slices, it turns out, well, of course, lambda and mu cannot be arbitrary. Like mu cannot be larger than lambda for sure. But it turns out that the necessary and sufficient condition for this lambda and mu to be parts of a 3D Young diagram is precisely this interlacing condition. So this interlacing thing hints at something which happens in 3D. And something indeed happens in 3D, but I don't have time to talk about it. Okay, thank you very much.
think you can guess what is my question. It is on the 7 brains.
Yes, yes. So the 7 brains are McMahon representations. There is a representation for them, and there is an R matrix. So if I have to draw them in some way, like that. So this will correspond to a 7 brain. They also have PQ labels. So this is supposed to be 0, 1 of 0, 1 type. And this corresponds to M representation of A, or, okay, also called McMahon, like this McMahon representation is called for because the states are labeled by 3D Young diagrams. And the reason are metrics for this. You can solve for an operator like this. And what happens here is a bit of a mixture of these two conditions on pi. If you have pi and draw here, pi and draw should also satisfy something. This is
This hints to
yes, yes. We can discuss it later.
Okay.
We can discuss it later. Yes, it does hint to exactly what you are thinking about.
More comments? Remarks? Questions? No more? Okay, let's send speaker again.
Okay.